Okay, good afternoon to one and all. We are almost at the end of the third chapter. And before directly going to that chapter, I just want to rewind the entire third unit and listen carefully. And this is going to be your revision for your mid exams also. Okay. Our third unit is mining frequent patterns, association, and correlation. So first of all, my voice is audible, right? Hello.
Yes, ma'am, audible, ma'am.
Yeah, thank you. So first of all, what is meant by pattern? It is the sequence of action, helps in future prediction. And coming to the, just I'm going to brief in the third chapter only. I'm not going to going into the details. Coming to the frequent pattern. So frequent patterns occur frequently by satisfying a given threshold. So such a patterns are referred as frequent patterns. And frequent patterns may be the item set subsequences of substructure. So finding frequent patterns helps in mining associations, correlations among the data. And coming to the association rules, these are the extent form of statements. And here the goal is to mine strong rules from the data by satisfying the measure supported confidence. And a well-known example of association rules is market basket analysis. And here is an example of the association rule for a given data set. For a person buys a laptop, then he is going to buy the antivirus software with certain support and confidence. This is a form of the association rule. So for a rule x implies y, the support is given as the probability that a transaction containing both x and y, whereas the constant is given referred as the conditional probability that a transaction containing x also containing y. So if a rule satisfies both minimum support and context thresholds, such rules are called as strong rules. Such rules are called as strong rules. And here is an example. Consider a data set given here and consider the rule A implies P. Then what is the support? How we can obtain the support of this? Support is given as the probability that a transaction containing both the x and y. So here out of four transactions, how many transactions containing both x and y? X and y in the sense here A and C. So out of four transactions, only two transactions containing A and C. So here the support is given as 50%. Similarly, what is the confidence? So here confidence, what is the confidence? How we can get the confidence? It is the conditional probability that a transaction containing X also containing Y. So here, how many transactions containing A? Here we find there are three transactions containing A. So out of three, how many contains C? Only two transactions containing C. So here 2 by 3, which is nothing but 66.6% is the confidence. In this way, we can obtain supported confidence. And here also, for this example, you can obtain the support and confidence of the rule laptop implies antivirus software by using the same formula. And here is the market basket analysis. It is the technique of data analysis used for marketing purpose. The idea is to analyze the buying habits of customers by observing his shopping basket to uncover what items are frequently bought together by the customer. Here, presence or absence of an item is item in the basket is indicated with a Boolean value. Each basket is represented as a Boolean vector. The Boolean vector is analyzed to identify buying patterns, and these patterns can be represented in the form of association rules. Here is the pictorial representation of the market basket analysis. And coming to its applications, cross-selling, product placement, catalog design, which is also called the store layout, loss leader analysis, all these are the applications of the market basket analysis. So if you want in-depth details of all these topics, you can refer the YouTube which you have for your section, because each and every recorded class is posted in the YouTube. So for in detailed explanation, you can go to that. So we are having different association rules exist, and if the association rules, if the association rules involve items from multiple levels of abstraction, then it is what is multi-level. Yes, then it is multi-level association rule. Otherwise, it is single association rule. So if you consider this, here in this association rule, we are having an item computer and we are having an item HP printer. So computer is from higher abstraction level, HP printer is from lower abstraction level. So if a association rule consisting of item sets from multiple levels of abstraction, those kinds of rules are referred as multi-level association rules, whereas the other rules which are obtained from which consisting of the items obtained from a single level of abstraction, those are called single level association rules. So we are uh, this is the concept belonging to the concept hierarchy. Okay, and next, based on the number of data dimensions involved in the rule, we are having single dimension association rule, multi-dimensional association rules. Coming to the single dimension association rules, if a rule consisting of only single dimension of variable or attribute, whatever, so that rule is called as a single dimension association rule. Or if a rule consisting of more than one dimension, here age is one dimension, income is one dimension, and vice is one dimension. Like this, if a rule consisting of more than one dimension, then it is called multidimensional association rules. And based on the type of values handled in the rule, again we are having here Boolean association rule and quantum association rule. So market basket analysis, the rules belonging to that is an example of Boolean association rule. And coming to the quantitative, if the rule include the quantities, if the rule includes the quantities like this, then such kind of rules are belonging to the quantitative association rules. And coming to the frequent item set, if an item set is frequent item set, its frequency of occurrence should satisfy minimum support count. If you consider this example, here is an data set, and these are the possible item sets from the data set. So what is the count of A? Here A is occurred 3 times, B is occurred 2 times, and AB item set AB is occurred 9. And given the minimum support as 2, so based on this minimum support, we can tell that whether the item set is frequent or not. We can decide whether the item set is frequent or not. So here, since the count of A is greater than or it satisfies the minimum support, it can be referred as a frequent item set, and this is also a frequent item set. Whereas the count of AB is less than the count of minimum support, so it is not a frequent. This is infrequent item set. So like this, we can find the frequency of the find the frequent item set. And here we need to discuss about the downward closure property. If an item set is frequent, then all its subsets are also frequent. Remember this. This is the downward closure property. And coming to the closed and maximal item sets. So association rules generation is a two-step process. And first we need to find all frequent item sets. And next we need to generate strong association rules from that frequent item set. So in order to generate the strong association rules, first we need to find all the frequent item sets. So from the downward closure property, we are having multiple too many number of subsets for a given frequent set. Why? Because if the length of the frequent item set is k, then all of its 2 power k minus 1 subsets are also frequent. So handling these many frequent item sets is highly difficult. So in order to get rid of this, we are going for two methods: closed frequent item set and maximal frequent item set. Here is the closed frequent item set. Is my voice is visible to are you getting my voice?
Yes, ma'am.
Yes, thank you. So coming to the closed frequent item set and maximal frequent item set. So here there are two rules for these closed frequent and maximal frequent item set. For a closed frequent item set, the first rule is X should be frequent. If an item set X is closed frequent, The first and foremost rule is it should be frequent. And next, no immediate superset of X has same support count as X. And again, for this also we are having two rules for decide whether X is maximal frequent item set or not. The first one is X should be frequent, and the next one is no immediate superset of X is frequent. So for both these things, the first rule is common. X should be frequent. So in order to derive whether the item set X is closed frequent or maximal frequent, first it should be frequent item set. So that is the first step. Let us go in detail by taking an example. Here is an example data set, and by substituting in the formula, we are having 31 subsets we are having. So all these are the 31 subsets we are having. So out of 31 subsets, first we need to decide. First, we need to filter out all infrequent item sets. Why? Because the first condition is X should be frequent, right? The first condition in both closed frequent and maximal frequent item sets is X should be frequent. For that, we need to remove all infrequent item sets. So how to find the frequency based on the given minimum support? Here in this example, the given minimum support is 2. So based on the given minimum support, we need to find out the frequency of the item set. If at all it is frequent, then we can kept it, or otherwise we can remove it from the list. So after doing this, we are having out of total of 31 item sets, we are having 15 frequent item sets and 50 infrequent item sets, and the corresponding label is given in the third column. Given in the third column, F indicates the frequent item set, whereas I indicates the infrequent item set. And here coming to the first one, closed frequent item set. So now after now we are filtering all infrequent item sets. So we have done with the first step. So now we are in the second step. What is that? No immediate superset of X has same support count as X. So first we need to find out the immediate supersets of X. What is that immediate superset? The immediate superset of X should have the length more than 1 compared to the length of the X item set X. For example, if A is the item set, its length is 1, right? So its immediate superset should consisting of length 2, like that. If the item set consisting of, if suppose this is the item set, its length is 2, then its immediate item set should consisting of length 3, like this. So here first we need to, if suppose this is my X, this is my X. So I need to find out whether this is closed frequent item set or not. So for this, what we need to do? We need to go to its immediate superset. So what are the immediate supersets? AB is an immediate superset, AC is the immediate superset, AE, right? So we are having three immediate supersets, AB, AC, and AE. Next, we need to find out what we need to find out. No immediate superset of X has same support count as X. So now we need to find out support counts of the immediate superset. The support count of AB is 2, which is less than this, so there is no problem. Here it is 3, which is equal to this, So it shouldn't be close to frequent. Just wait for a while. No immediate superset of X has same support count of X. Yeah. So it shouldn't be closed frequent. So it is not closed. Why? Because it's since even though AB satisfies the second condition, AC does not satisfy. Why? Because it's consisting of the same count as A. So we can stop with this, and we can conclude that this is not closed. And similarly, you can go for B. What is the immediate superset for B? AB is the immediate superset, and similarly BC and BE. All these are the immediate supersets. And the count of B is 4. What is the count of AB? 2. Since it is less than 4, you can it satisfies the condition 2. And next BC, count of BC is 3. Since it is less than 4, it is also satisfies the condition 2, second condition, that is this one. Whereas the count of B is 4, which is equal to this actually. So it fails the condition 2. So according to this, it is not closed. So like this, for each item set, you consider each item set as X, and you can go for its immediate superset consisting of length more than that. And based on the by satisfying the second condition, you can decide whether it is a whether it is a closed frequent item set or not a closed frequent item set. Like this, we are mentioning NC if it is not closed, or C if it is closed, like this. So like this, you can find whether the item set X is closed frequent or not, and here is a maximal frequent item set. So here also, what's the condition? No immediate superset of X is frequent. So to decide whether the given item set is maximal frequent or not, here the condition is no immediate superset of X is frequent. So here our task is to find out the immediate superset of X. So here, if suppose this is our X, what is the immediate superset of X? Immediate superset in the sense AB is the immediate superset, AC is the immediate superset, AE is the immediate superset. What's the condition? No superset, no immediate superset is frequent. But we know that all these are frequent because we are only consisting of the frequent list only. So the immediate superset is frequent. We can conclude that this is not maximum. We can conclude that this is not maximum. Similarly for B, its immediate superset is AB and this is frequent. So this is also not maximum. So unfortunately for this example, we have considered here all are not maximal except the last one, because it's consisting of no superset. We can conclude that this is maximum. Like this we can calculate, but this is not the case for all the all examples. For this example, we got like this. So like this, we are having out of 15 frequent item sets, we are having 5 closed frequent item sets and 1 maximal frequent item set. And from this observation, we can conclude that the maximal frequent item sets are subset of closed frequent item set, which is subset of the frequent item set. And here to improve the efficiency of the mining frequent item sets, we are having two methods, a priori method and FT flows. I think you are already familiar with these two methods, why? Because the same concepts you have already studied in your previous semester, right? And coming to I'm going to briefing the concepts again. It's my responsibility to briefing again. Okay, coming to the a priori method, it is applicable for Boolean association rules only, and it employs a level-wise search approach. And set of frequent one item set C1 is found first, and after that from C1 we need to generate L1, and again from L1 we need to generate L2. Like this, it follows some level-wise search approach. And here we are having a priori property, which is that if an item set is frequent, all its subsets are also frequent, or if an item set is infrequent, all its supersets are infrequent. We have two steps here, join step and prune step. Especially in the prune step, we have used the a priori property or a principle. So here is an example. Here initially we have considered for the considered data set, we need to scan the data set for mining all the frequent one item sets, and after that we need to infiltrate. That means we need to filter all the infrequent item sets, and we need to mention only the frequent item sets here, and which is nothing but the L1. And after that L1, by applying the join step, we can generate the candidate two item sets. And from that candidate two item set, again we need to scan the database to mention all its supports. And again you need to go for minimum support count, and you need to infiltrate or you need to filter out all the infrequent item sets, and which resulted in L2. And after that, from L2 again, just like done here, from L2 we need to generate again candidate three item sets. So what's the next process? We need to generate candidate three item sets by self joining L2 with L2. If you did this, you have generated these many candidate three item sets. And here, what is the actual process? Actually, when you generate the candidate item set, again we need to have a database scan, and we need to retrieve its support count. This is the process. But instead of doing this, here we are applying the a priori principle. Instead of going for the database scan, for scanning the identifying the counts of these many items, you can filter here some of the items by applying the a priori principle. That is a priori principle. You are applying that in the prune step. So what we are doing according to the a priori principle, if an item set is infrequent, then all its supersets must be infrequent. So for this, what we are doing for each and every item set, we are generating the equivalent subsets first. We are generating the equivalent subsets. So according to the a priori principle, if an item set is infrequent, for example, consider these are the item sets. If an item set, for example, this is infrequent, then all its supersets must be infrequent. So if it is infrequent, its superset is also infrequent. If all these three are frequent, then its superset is also frequent. If any one of the subset is infrequent, then its superset is also infrequent. Like this way, you can filter out all the infrequent three items. So how we can how to know how to find whether the particular item set is frequent or not from L2. So if at all the item set is exist in L2, then it is frequent. So we can assure that this is frequent or this is infrequent like this. So if at all the subsets are all the subsets are frequent, then its superset is also frequent. So like this way, by with the help of L2, with the help of L2, you can filter here, and we are resulted with only two item sets. We are resulted with only two frequent item sets. So after that, we need to go for the database scan to find out the support counts for these two item sets. Which after that, we need to go for the L3 by further checking whether these are frequent or not. We need to generate the candidate three item set, and after that, since there is no candidate four item set, frequent candidate four item set exists, we can stop here. So this is the actual a priori principle, and this is the restricted algorithm. In exams, you need to write the algorithm also. I have explained the algorithm clearly in the original classes. Since this is a revision class, I am skipping this slide. So if you want this explanation of the algorithm, you can go for the recorded videos which are available in the YouTube. Okay, I'm moving next, and this is the overall procedure we have done for the a priori, and we are having some methods for improving the efficiency of the a priori. Okay, coming to the hash based technique. So it is especially to reduce the size of the candidate set, especially for k is equal to 2. Why? Because here we have implemented a priori principle for k is equal to 3. But at k is equal to 2, we won't apply any a priori principle, right? So especially for reducing the for enhancing the efficiency of this second iteration process, we are going for the based technique. So here, while scanning the one item sets at the beginning, all the two item sets are retrieved and hashed into the bucket based on the hash function. By observing all the bucket counts, we can retrieve all the frequent two item sets. And coming to the transaction reduction. So here we are removing all the transactions that does not contain frequent k item set, as it cannot hold frequent k plus 1 item set. And coming to the third one, partitioning. It is to reduce the number of database scans. It is especially for that. And here the entire database is divided into unequal parts, and for each equal part, we need to find out the local frequent item sets for each partition. And after that, we need to combine all the local frequent item sets. And this is the first phase. And in the second phase, again, we need to go for the second scan of the database. And here we need to find out all the global frequent item sets from the generated local frequent item sets. In this way, you can enhance the efficiency of the a priori method. And the next method is FP growth. Why you to go for the FP growth means we are having some deficiencies in the a priori. Especially a priori suffers from two non-trivial costs. One is generation of huge candidate sets, too many candidate sets, and the second one is too many database scans. So it demands another alternative method, which is nothing but FP growth. So here it first an FP tree is generated, and from that conditional pattern basis was generated. This is the process we are going for the FP tree. So here how to generate the FP tree first. First, we need to consider a previous example. We are considering the previous example only, and here first we need to retrieve the all candidate one item set, and after that we need to sort it based on the support counts in ascending order, And from that sorted table, we need to consider the sorted table, and that how to draw this SP tree. I'm going to give a brief idea. How to sort this? First, we need to consider each item. Uh, First, we need to consider each item set, and we need to rearrange it according to the sorted order. So, if you rearrange it, it becomes I2, I1, and I5. So, this is from table. From table. This order is from obtained from table. So, first I2, next I1, and I5. So, I2. So, this is I2. So, initially we are having null node, and from this we are having I2 here, I2 to I1. So, with the count 1, initially we need to assign the count 1 from I2 to next I1. So, next we need to draw an arrow here with count 1 again from I1 to I5 with count 1. Like this, we are having a branch for the first transaction. And coming to the next transaction, I2, I4. So we are already having I2 as a direct link from the root node. So just what we need to do is we need to just increase the count here, and from that I2 to I4. So again we're having I4 here. So there is no I4. Now we need to draw the I4 here, and we need to mention the count as 1. Like this, we need to trace each and every transaction, and we need to draw the tree from the transaction. So which resulted in an FP tree. So here is the FP tree resulted from that above process, and from that we need to generate the conditional pattern base. How to generate that? First we need to write from the bottom to top. First we need to write from the bottom to top. Consider I5. So here, how to get the I5? There are two I5s exist in our tree. There are two I5s exist. First I5, the path is from I2, I1, and I5. The path is from I2 and I1. And the second I5, for the second I5, the path is from I2, I1, I3. So the path is from I2, I1, and I3. And here is count 1, and here is the count 1. Like this, you need to first fill the first column, which is nothing but conditional pattern base. And coming to the second column, conditional FP tree. How to construct this? So here, based on this, here we are having two I2s.
ఒకసారి వినండి. మేడం వచ్చారా? హలో,
లెఫ్ట్ అయిపోయారు సార్.
స్టార్ట్ అయిందా మామూలుగా 2 o'clock?
స్టార్ట్ అయింది సార్.
మధ్యలో ఆగిందా ప్రాబ్లం వచ్చి?
మధ్యలో ఆగిపోయింది సార్.
సమీరా మేడమా?
అవును సార్.
ఓకే.
నా స్క్రీన్ మీకు కనిపిస్తుందా? హలో,
స్క్రీన్ కనిపించట్లేదు మేడం.
మానస్ సార్,
మేడం
మీరు హోస్ట్ గా జాయిన్ అయినట్టుంది. ఒకసారి నన్ను హోస్ట్ చేయండి, నా స్క్రీన్ షేర్ ఆప్షన్ పోయింది అనుకో.
మీ తర్వాత జాయిన్ అయ్యింది మేడం. మీరే హోస్ట్, నేనా?
కాదు, ఇక్కడ ఎందుకో మిమ్మల్ని హోస్ట్ చూపిస్తుంది ఇంట్లో.
ఓకే ఓకే మేడం, డన్.
Is my screen is visible?
Yes, ma'am.
So till this slide, everyone is able to follow till this slide. Hello, is my voice is audible or no?
Audible, ma'am.
ఈ స్లైడ్ వరకు ఫాలో అయ్యారా?
అయ్యాం మ్యామ్.
షూర్ కదా? ఇప్పుడు ఈ స్లైడ్ వరకు ఫాలో అయ్యారు కదా?
ఎస్
ఓకే, థ్యాంక్ యూ.
అవును మ్యామ్.
Okay. Multi-level association rules. So if the rules are if the association rule consisting of item sets from multiple levels of abstraction, then it is multi-level association rule. So in general, it is difficult to find interesting patterns at lower levels of abstraction. Hence, data can be generalized by replacing low-level concepts with the ancestors. So if you consider this rule 1, here you can say that rule 1 is an ancestor of the rule 2. Why? Because rule 1, the item computer and printer is extracted or belonging to the higher level of abstraction, whereas the items IBM laptop, computer, and HP printer is extracted from the lower levels of abstraction. So here we can say that rule 1 is an ancestor of the rule 2. So in this case, it is very difficult to extract interesting patterns or association rules from the lower levels of abstraction. So here in this case, we can generalize the concept. So mining of multiple association rules can be done in 3 ways: uniform minimum support for all levels, reduced minimum support at lower levels, item or group based minimum support. So here for the first case, uniform minimum support for all levels, we are giving certain uniform minimum support for all the levels. So with this, what the drawback is, if the minimum support is given, minimum support threshold is given too high, then what happens? If the given minimum support threshold is too high, then it may miss some meaningful associations occurred at the lower level of abstraction. If the support threshold is too low, then what happens? Many unnecessary, many uninteresting rules are extracted from the higher level of abstraction. So that balance should be maintained. And here is this is a little drawback with the giving uniform minimum support for all the levels. And coming to the next one, reduced minimum support at lower levels. So here we are giving some higher minimum support for the higher levels, and we are giving some lower or reduced minimum support for the lower levels. So with this, we are satisfying the constraints, both the constraints of higher levels and lower levels, so that finally we can retrieve some meaningful associations from both the higher level of abstraction concept hierarchies and lower level of abstraction concept hierarchy. And the third category is item or group based minimum support. So here we are giving some minimum support, not based on the concept hierarchies, only based on the items or groups. For example, the items, rarely purchased items like diamond, watch, gold, etc., are giving some very minimum support compared to the items like bread and milk, which are frequently purchased. So this is the item or group based minimum support. And coming to the next topic, redundancy filtering. Due to the ancestor relationship, redundant rules are generated which should be filtered. So here, as I said earlier, here R1 is the ancestor of R2. Actually, we can say that these two rules are redundant based on constraint. What's that constraint? If a rule is redundant, if its support is close to the expected value according to its ancestor rule, and it has the same similar confidence to its ancestor. So since these two rules, R1 and R2, satisfies this condition, we can say that these rules are redundant. So if at all a rule is redundant, you can remove the second rule. You can remove the second rule by keeping the ancestor rule. Why? Because this rule says the broadness. This rule represents the high level of concept hierarchy. So you can keep that rule and you can remove the redundant rule. And coming to the next one, mining multi-dimensional association rules from relational databases and databases. So what is a multi-dimensional association rule? We already know that if a rule consisting of the single predicate, that is a single dimension. If a rule consisting of multiple predicates, that is multi-dimensional association rule. So here if a predicate, if the same predicate occurs more than once, then it is called as intradimensional predicate. So here, if in a multidimensional rule, if there exist all different dimensions, then that belongs to the interdimensional association rule. Or in a multidimensional association rule, if a predicate or dimension exists more than one, if a predicate or dimension exists more than once, then that is a hybrid dimensional association rule. Then that is a hybrid dimensional association rule. So here two types of multidimensional association. There are two types of attributes are there: categorical attributes and quantitative. We already know that categorical attributes are the values which are not orderable. For example, name, branch, section, etc., etc. Whereas quantitative, as the name itself indicates, these are the numbers which can be ordered. The example, rank, marks, years, etc. So here there are two basic approaches for handling or for mining multidimensional association rules based on the handling of quantitative attributes. Those are static discretization of quantitative attributes and dynamic quantitative association rules. And so here we are having two methods of mining multidimensional association rules based on the way of handling quantitative attributes. So coming to the first one, static discretization of quantitative association rules, quantitative attributes. So here the quantitative attributes are discretized. Right. So here the quantitative attributes are discretized using data discretization techniques. Here the discretization is static and the resultant attribute become the categorical attribute. The resultant categorical data is represented using data sheets. So here is the lattice of cuboid exists. Coming to the dynamic discretization of quantitative attributes, here numerical attributes are clustered into bins. So the resultant attributes are treated as quantities rather than categories. The rules mined in this approach are referred as dynamic quantitative association rules. So here the aim is to mine 2D quantitative association rules using association rule clustering system. So that is ARCS. So here we are using the ARCS method. So ARCS maps quantitative attributes onto a 2D grid. After that, the grid is searched for the clusters, and these clusters are further used to generate association rules. And it is a three-step process. It is actually a three-step process. Coming to the first step, which is binning, here dynamic intervals are made on the quantitative. The three steps are binning and finding frequent predicates and clustering the association rules. And coming to the first step, which is binning, here dynamic intervals are made on the quantitative attributes. And these intervals are called as bins. And here we are having different binning strategies: equal width binning, equal frequency binning, and clustering based binning. So as the name itself indicates that equal width binning. Equal width binning, here it maintains the equal interval size. Coming to the equal frequency binning, it maintains that the number of items fall under each bin should be same. That means the frequency of items fall under each bin should be same for the equal frequency binning. And coming to the third one, clustering based binning. Here for the clustering based binning, the neighboring points on the grid are grouped as bins based on the clustering procedure. So for this, it needs to apply some clustering algorithms, which are covered in the next chapter. Okay, and coming to ARCS, it uses the equal width binning. A 2D array is created for each possible bin combination, such that each cell holds the class counts. And coming to the second one, finding the frequent predicate sets. So to find the frequent predicate sets, the 2D array is scanned based on the minimum support and minimum confidence threshold. And after this, strong association rules are mined on top of these frequent predicate sets. And coming to the third one, clustering the association rules. To cluster the rules, the formed association. So in order to cluster this, here, in order to cluster the association rules, the formed association rules are projected in grouped as clusters based on the neighboring points. Here in the figure, it shows that it shows a 2D grid, 2D grid for 2D quantitative association rules, predicting the condition bias of x comma HTTV. That means if a person x, whether he buys the HTTV or not. So given the quantitative attribute age and income. So here from the grid, the same grid is mentioned in the next slide also. So here from the grid, you can form some clusters by observing. So you can form some clusters by observation. So what is the first rule you have extracted here? X with the age 34 and income with the range 31 to 40. He may buy the HD TV. So here X with the age 34 and income with the range 31 to 30K buys the HD TV. So it indicates this cell. So it indicates this cell. Again, coming to the second rule, X with the age 35 and with the income 31K to 40K. So with the age 35 and the income 31K to 40K, it indicates this cell. And again, coming to the third rule, X with the age 4 and income with income of 41 to 50K. So age 34 and income of 41 to 50K, it indicates this cell. And similarly, the last rule indicates this cell. So by projecting the rules, by clearly observing this grid, we can form some clusters. So by observing the clusters, we can, since this is the dynamic discretization process, this is not a static discretization, we are in the dynamic discretization process, we can change the intervals, change the bins in order to extract the strong rule. So these four rules form a rule cluster on the grid, right? So these four rules can be combined together to form the simpler rule. This is the simpler rule which is generated. That means X with the age of 34 to 35, right? This is the range. And income with the range of 31 to 50K. This is the range. If this is the criteria, then X can buy the HTTV. So this results in a dynamic discretization of quantitative attributes. So for this, ARC should employ a clustering algorithm, as I said earlier. Okay. And here we are gradually entering to the entering into the correlation mining from association mining actually. So what here the criteria is not all strong rules, strong association rules which are mined are interesting actually. Here the scenario. So why the strong association rules are, why all not association rules are not interesting? Why? Because there is a criteria here. So this is completely the different topic. I will continue this. I will continue the next class from this topic. I'm going to end up this session for now, and I will extend the time for submitting the assignment. I will post the time in the group. So those who are not yet submitted, ready with your assignment, and you need to post that in the Edmodo, and the last date for the submission is I will mention you in the group, and those who are prepared the assignment should bring the hard copies when you are coming for the internal exam. Okay, now I'm going to end up this class. And is there any doubt regarding this session? If nobody have any doubts, you can leave the class. Okay. You can leave the class now.